Okay. Morning, everyone. So this is going to be more of a tour. There's going to be some code, but I'm just going to kind of walk you through all the different ways that I've built stuff on top of YT for geo stuff. Also, some of the Napari stuff we'll look at a little bit too. So the and all of this, these notebooks are up in the workshop repository, but I'm actually going to go through them backwards. Just hit the things that I haven't talked about more. So the first thing will be pretty short, but so YT Aspect is a YT front end that I wrote for Aspect, which is a mantle convection code. So it's a finite element base. They have adaptive mesh refinement in it. They run both Cartesian and spherical simulations, and the outputs are generally in PVTU files, which are unstructured mesh files, one of VTK's file formats for parallel computation, where the chunks of the mesh are split up across files. So YT Aspect is an externally packaged front end for YT, and that just means that it lives in its own repository, has its own releases. You install directly from there, but once you install and import it, it's available like any other front end. I don't know, Matt, maybe you'll talk about that in the first little bit, but I found it it's like a much quicker route to distributing your front end and trying to get it into main YT. So it's nice to get something up there, make it available, and kind of iterate on before maybe someday bringing it into main YT. Yeah, so let's just take a look just to reinforce what we're loading in here. So this is just a benchmark solution that I ran for it's a 2D spherical shell. So the solution is in spherical coordinates, but the actual output files in the PVTU are all converted to Cartesian coordinates. So it makes it very easy to load into YT in the unstructured meshes. It's a Cartesian data set. And a single solution is kind of all the metadata for it for a time set is at the top level PVTU file, and then all of these other VTU files for that time set just are all the chunks of the mesh. And in writing this little code snippet last night, I realized that we have not talked about YT configuration at all. So I thought I would take this moment just to mention it because I'm using it here to make things a little bit quick. So there's a long documentation page on it, but basically you can write a configuration file that lives either in your home directory or your local directory, lets you do a lot of things for YT. The thing I use it most for is in this line up here, there is this test data dir option, which is effectively just adds a directory to YT's search path when it's loading. And so I keep all my data under a certain partition in my laptop, and I have a data directory there. And every time I type yt.load, it searches there in addition to the local directory. So I find that very useful. There's also a lot of really cool stuff you can do, especially with customizing what happens to fields. The per field plot option. So you can set color maps, default log, for, normalization parameters, and then default units for things. And so anytime you plot one of those fields, it'll pop up with, or the initial plot will have that configuration applied already. So that is very useful. I also learned last night that if you import your config and just print it to screen, Jupyter will give you back screen just like how everything is actually set, which I did not know until yesterday. Kind of convenient.
Cool.
I don't know if we did that or if that's that's something that we did. I don't know, but it's nice. Okay, so back to Aspect. So to use an externally packaged front end, you import YT and then the front end. I don't think the order matters, but after you import your front end, it registers it with YT so that from there on, it's as if it's just in main YT. You won't notice any difference. So you can use yt.load to get your data in. This is not a very big data set, just a couple fields, temperature, pressure, velocities. And so let's make a nice plot. Oh. There is a mantle, doing nice convection, get some nice convection cells, and then the faint white lines are the mesh that's overlaid on top of it, the mesh lines. So it's obviously it's adaptive mesh.
So can we just walk through it for a second? So this is AMR, this is adaptive mesh in non-Cartesian coordinates
Yes.
from a ETVU.
Yes.
ETVU file.
But the way that they export to the PBTU file, it exports the elements in Cartesian. So it does that transformation already. So from YT's perspective, it's a Cartesian data set.
Interesting.
Yeah.
But you're overplotting non-Cartesian cells, it looks like.
Yes, because the cells are stored. They're stored in Cartesian boundaries, but like, they're like.
They're logically Cartesian, but.
Yes.
What do you mean it's sort of?
So they do the solution in spherical coordinates, but when they export, they transform to Cartesian. So they transform their cell boundaries and everything to Cartesian coordinates.
Oh, okay.
Store in the PBTU files. Which I think is mainly a historical thing because they've used peer review for a long time for everything, and it's just easier to do that. But it's certainly easier for us to load it at too.
I was stupid. Is it really the temperature?
Yeah.
4 kelvins? Oh, 10 to 3. Okay, never mind.
Yeah. Close to 500 at the core mantle boundary out to, I don't know what their outer boundary condition. Oh, I guess it's probably not actually the surface because it's 1000 Kelvin. So probably like 800 kilometers beneath the surface. That's cool. And then just to show you like a fun other example, a 3D example. So this is a simulation of emergent fault structures when the lithosphere is extending and falling apart. So the simulation, they see weaknesses in the lithosphere in a certain zone and they stretch it and look at how zones of deformation coalesce into faults. And data courtesy of one of my colleagues, John Alaboff, which I couldn't actually find where I kept the data file. So I was going to load it up, but we're just going to look at this image that I have previously made. So this one was done with YT's unstructured mesh rendering, which I did not talk about yesterday in the volume rendering session. It's a little bit different in that it's not true volume rendering. It's opaque. It's volume rendering, but sources are opaque in the unstructured mesh rendering in YT. So you can't use transfer functions, but you can do some fun stuff with like cutting planes and stuff to make different images. This also used the optional ray tracing acceleration from Embry that YT supports. If you're interested in that sort of stuff, go check out the docs on the unstructured mesh rendering. And also, finally, I will say, if you have unstructured meshes, there's a fair bit of development that YT would benefit from. So the highest priorities that I see are a proper data chunking scheme. Because currently, you have to concatenate across the chunks in order to do the plot. It would be really nice to actually properly implement the chunking routine so that all the AMR and octree handling, it plots by chunk. And then I think it also would be really nice to have full volume rendering with transfer functions, which are both attainable, just development time mainly. So that's YT aspect. And backwards. Okay, so pushing gears a little bit, I can tell you a little bit about YT Napari, which I showed a little bit yesterday. Not exactly geo, but it is kind of a broader package that is you can use with all your astro data, but you get access to a lot of cool stuff from the bioimaging community. So, yeah, so YT Napari is an extension for Napari. Napari is a Qt-based multi-dimensional viewer. Let me actually run that and open. And this laptop takes a little bit. So this is our Napari interface here. Yesterday, I showed you a little bit about how you would load in data from a notebook. So you would load in your data set, start up a scene object from YT Napari, and then use that to add all of your layers to the Napari interface using this add region, where it will go and pull out fixed resolution arrays to add to Napari. And that's probably how most of you would use it, I would imagine, if you're working from notebooks. But there are also other ways to load data out in docs. So you can actually write JSON files like this, where you provide a schema that describes how you can enter data selections. So you provide file you want to load from, and then data selections you want to load. And then you can just load that file. Yeah.
I just want to add, whenever you've got a JSON file, so JSON files are notoriously difficult to edit because it's easy to make errors and whatnot. But VS Code, any Monaco based thing, if you've got a schema definition, will do autocompletes and error checking and so on. And so like being able to write a JSON file with the schema that Chris has developed is pretty rad.
And I haven't actually done this, but I imagine there could be some fun use cases with like deploying little Napari like viewer instances for Wiki data sets, where because you could write a set of JSON files for loading different data sets pretty easily as Electron. But yeah, maybe you'll come up with other uses for it. And then the other way to load in data, so in Napari, when you install plugins, they show up in this plugins thing. I have a bunch here because I was experimenting with some last night to show you. But there's after you install YT Napari, there's a YT Napari entry, and there's a couple of things. So this YT reader is essentially all the fields that you can enter into the JSON file just in a UT plugin in the environment if it decides to pop up. And for some reason, Napari on this laptop has been a pain to work with. Okay, so you select file, just do it. So they did Elixir. Other than showing you all my directory structures, I'll just type that in. You want to add in a region, you can also do slices or covering grids, gas, density, take the log. You can set the left and right edges of your selection, the resolution. You can add additional regions if you want, which don't have to cover the same extent. It'll kind of handle all the registration to make sure things line up. There. Take the log. We get out our galaxy, which by default loads up in grayscale. Click the bottom down there to switch to 3D, and we get our galaxy problem, which is pretty low resolution just because I wanted it to go fast for the spurts. Cool. So other things you can do with this. You can do some time series analysis in this in YT Napari. So I've added the ability to do this with Dask because in YT Napari you can load image stacks with Dask, and when you switch between images, Dask will go and fetch the image that you need. So you don't need to load everything in memory beforehand. So YT Napari has this time series object that has a similar add to viewer function where you specify object that you want to actually apply to each individual time step. So in this case, we're going to slice through every time step at some resolution. And then you provide a file pattern to identify all the time steps that you want. Load this as an image stack using Dask with some defaults applied to settings. YT Napari variably implements threading stuff just because like threading with YT can be kind of hard to manage. So often the YT Napari calls will block the loading everything. Okay, that shouldn't be happening. It's actually processing the whole time series and loading up the slices for some reason. Okay, well, that might be a bug because I haven't looked at it recently, but last night I have done. Luckily, I did slices and not regions, so. small. Crash my computer. So I'll just wait for the result. It will be too long. Remember how many steps are in Zotiny cosmology? I feel like we must be close to the end.
It's 40, yeah, it's 47 if it's just TDs. Oh, now we're doing the RDs.
Oh. Something might be wrong with file selection then.
Oh, no, they won't. Maybe they're just not in order.
Oh, yeah, they are not in order because
Okay.
CAS will just distribute things.
Okay,
So I think it's just computing all of them.
you're nearly there.
Okay, let's wait it out then. Yeah, Napari is ready. Let's see what we got. Okay, oh, you know why? I think because I was in a 3D view when I loaded things, and so in order to do that, it has to load all the slices. Let's switch back to 2D. I should have made sure of that. So since everything's in memory, this should be pretty snappy, unless it might. Yeah, it might jettison them. And the party is just being slow. So here we go. So now we're clicking, you can click through slices, same slice across all the time slices. So you can watch the evolution on a slice with on a faster laptop. This is like, maybe about a second delay. It's not too bad on this, but a better powered laptop can generally handle this pretty smoothly. But yeah, so that's fun. Time series. And then the other part to this, which I think is kind of the cooler part, is all of the access you get to the wider Napari ecosystem. So Napari has a large number of user contributed plugins that primarily come from the bioimaging community. And so most of that focuses on things like image segmentation and classification. So running like automated identification of cell boundaries to look for like cancerous cells, and then look at how other fields relate to it, which are kind of fun to use with some of these data sets from YT. So for example, I'm going to show you a simple one that I can run pretty quickly on this laptop. So I'm going to add in 2 regions here, and that's, oh, nope. And so we're going to load in some single time stuff from Enzo 64, load in a density and temperature layers for that. And we're going to use the simple ITK plugin, which, yeah, so the Napari simple ITK image processing package installs some bunch of filters and stuff from the ITK imaging library. So we have our gas field, our density field. That's fine. But now we plug in. And the do multiple threshold one is kind of fun and runs pretty quick. I think so. So what this is a filter that will you select which image you want to apply it to, and it'll go through and just kind of threshold the image into different data ranges and see what you get out. I do wish more of the plugins had little. So what you get out is this nice like org cube or something. That's what it looks like to me. So this is what in Napari what's called a labels layer, which is just for each pixel is assigned an integer label value. And so it was here we classified our density structure, so what we get out is the cosmic web sort of, but instead of fields we have labels identified as being within certain layers, and you can go up here and click show selected, and it'll just show single selections at a time. Up to 5, which is the smallest layer, you see kind of outline of the cosmic web there. And from there, you can do lots of stuff with these sorts of labels layers. Like one very simple thing you can do is go back up to napari, simple ITK, and there's all these things that apply to labels. So you can build contours out of these label layers. Label statistics is just a very simple filter where it'll take that label and look at any other image layer and then run it, and it'll give you information about that image layer in each of those labeled domains. So you get like means, maxes, medians, standard deviations of things. And we generated this with the density, but we can also go look at any other field, and it'll tell you. For that again. Why is infinity on this? Well, principle, you should be able to do this and get out the same statistics for other fields that you did not, from different fields from which you generated the actual things. Yeah, and there's a whole bunch of other interesting plugins. Napari had a pretty large influx of funding from CZI, and so a lot of people were funded to actually create these plugins, and so some pretty big developer teams have worked on things. We were a small developer team.
You got two
Yeah.
different rounds of it.
Yeah, so that's how YT Napari happened. It was from CZI, but there's some like pretty slick GUI based things, and I'm not sure like actual research level. I'm not sure how useful it is because you got it to fixed resolution, so you lose some detail. But I think there's lots of potential applications in classroom settings. So trying to teach people some Astro stuff who may not know any coding, but you want to load in data sets and let them kind of look at it and move around. Yeah, so that was YT Napari. And then real quick, I think I've pretty much by this point shown you all the YT X-ray stuff that I kind of had showed you before. I'll just mention a couple of kind of features of it that I didn't really get to talk about in all previous times we've talked this. So just a couple links. There's the main documentation page, and there's also a recent presentation, Jupyter book presentation that I gave at NASA Software Workshop, which covers some of the stuff. So if you want to read more about it, you can check those out. And this is going to use one of the sample data sets we have up on the hub, which you could fetch yourself if you wanted to using this command. And this also requires a bunch of extra dependencies that don't come with your default YT relation. But yeah, so that's it. So first, one thing is that when using YT X-ray, there is this open data set which just aliases X-rays open data set, just so that I can add YT search paths to things. But what you get out is just the standard X-ray data set, which if you've not worked at it with it before, but one of the nice things about working with X-ray is you get a lot of metadata displayed for free without actually loading data. So, it gives us all the coordinates up front. You get a list of data variables, look through all those things, and you do all the normal X-array data set, so you can do all the normal X-array things like just plotting the single depth slice through the model. But once you install YT X-ray, there will be what's in X-ray terminology is called an accessor property underneath your main data set object. And a couple of things. So there's not too much there. So there are some convenience functions for some of the basic plots like phase plot, profile plot, projection plot, size plot, which will go and generate those things for you. And there's also this load grid, which will return just a YT data set that wraps the X-ray data set without copying data, so you can get things over to YT easily. So an example of doing this with the YT slice plot, you get back just a normal YT plot handle to which you can apply all the callbacks that you're used to. This is doing a little bit of extra with CartaPy just to handle the projection stuff. And we get our nice tomography map of the Western US. So if you run load grid and all of your data, all your arrays are just 3D, it just works generally. It's a little bit hard because X-ray can open any netCDF gridded data set. And so if you don't have like some standardized names in terms of your coordinates, you might have to add some aliases to YT X-ray so that it recognizes what to load as your XYZ. Or latitude, longitude. So, and a lot of data sets that come from like, especially like the climate modeling community, their netCDF files also have the time dependence within their data set file. And so usually to load into YT, you have to select time index that you want to add in there. And we check out our YT data set, geographic coordinates. And now that we have our full YT data set, we have our underlying X-array fields that we can plot, but we also have all of our derived fields. So for example, this is phase plot of our two variables weighted by the cell volume, which this is a non-Cartesian data set. Doing that would take a little bit of work in order to get your cell volumes because they're not uniform in Cartesian coordinates. But, and you also get projection plots, which I've played around with a little bit for seismic data. Actually, it's kind of a nice way to look at coherence of structure in the upper mantle in a way that people don't usually do. Like this is integrating one of the fields across the domain, which in this case is not a super physical quantity, just because I didn't have time to work out all the relationships from velocity to temperature to energy stuff in this presentation. But this feature here is the Yellowstone hotspot track, which if you look up just at the slices, depending on where you look in depth, it's more or less coherent across where it should be. So it's a nice way to look at those structures across them. And the final thing that I use it a lot for are these embedded transformations. So using all the loader stuff that we talked about the other day, you can effectively wrap an X-ray data set with a YT grid structure. And then on the fly, YT will go and fill in the values from your X-ray data set to that grid structure, which lets you do a lot of interpolation on the fly, which lets you load in spherical data sets as Cartesian very easily. So I'm not going to go through all of these, but there is some optional grid refinement involved too, because so this is a slice through the interpolated data set with some grid refinement. And so it adds a bunch of refined grids where it intersects with the data and saves a little bit of space by not, adding a little bit of a coarser grid outside where there is no data. Add a little field. It's just adding a field for where the data is defined and integrating across that just to see how there are a few grids where like maybe they could be truncated a little bit, but most cases it's decently represented across the data set. And run this a few times, but this is just the code for generating the volume rendering that I showed a few times, which would not be possible without this interpolation. Western US negative velocity anomaly map, which generally maps to temperature anomalies. But
Isn't that California?
this is the West Coast of California.
Yellowstone again?
This is Yellowstone. This absence is the Colorado Plateau, which is a section of thick cold lithosphere around which there's a lot of magmatism. And so some of these slow velocities are from a combination of high temperatures, but also the presence of magma that lowers the velocity of the seismic waves. This might mean not shafted or something. Anyway, cool. So that was the tour of. And I think I'm done.
Thank you, Chris. Alright, so we're gonna change things up just slightly. We'll take a coffee break now. And